We're now going to switch a bit into geometry mode, and I think especially these next few lessons will be a review for most of you. So this should go quite easily for now. These are some just big ideas that I think come pretty instinctively, but I'm going to formalize them a little bit. One thing that we may look at is finding the midpoint of a line or a plane or either in two-dimensional like on here, or of a line segment in 3 dimensions like this. And if you just were to consider this line segment in 2 dimensions, it's probably very easy to see approximately where it is. And that might be a really good idea to start. Essentially what we're going to do is we're going to find the halfway point of the x's to find the x coordinate and the halfway point of the y's, which is the y coordinate. So we're basically finding the average. So if I were to find the midpoint of this particular line segment, I could just look at the average between -8 and -2, or what's halfway between -8 and -2, and that's -5. You could use the average, like add them together and divide by 2 in this particular, in 2 because there's 2 ends. And the midway point of the y's, halfway between 4 and -3, is at a half. And again, we could have done 4 plus -3 divided by 2, so 1/2. And that same idea works when we want to find the midpoint of a line segment in 3 dimensions. We want to find halfway between the x's, halfway between the y's, and halfway between the z's. So you could find the average 1 and -4 divided by 2, the y's 2 and 10 divided by 2, and the z's divided by 2. And you may or may not even need to do this out like this. Of course, if you're given something algebraic, it may be advantageous to write out the equations though. So this would be the midpoint of this particular line segment in 3 dimensions. You may also have to find distance between 2 points, which is very, very simple as well. In 2 dimensions, of course, if the distance from A to B or B to A, it doesn't matter. And you see that we've created this kind of right triangle, and that distance of the right triangle is calculated by using the Pythagorean theorem. So if I find the difference between -8 and -2, I'll find this length, so that went over 6 units. And the difference between 4 and -3 is 7 units. Again, it doesn't matter what this is, because when I find the hypotenuse of a right triangle, I am looking at squaring things, and that will make them positive anyway, so it doesn't matter if I went down or up 7 units, or the left and the right 6 units. And you could find this just by subtracting. What's 4 minus -3? It's 7. That's the difference if you walk this. Okay. And when you find the distance of all of these, you'll get the C or D or whatever you want to call it, the length of AB. How about I write it like that, actually? That's probably wiser. Is equal to the square root of 7 squared plus 6 squared, or the square root of 85, which, if you wanted an approximation, is about 9.22. And this is going to be exactly the same in 3 dimensions. We don't really even need to draw it out. It's up to you to determine if you want to find the difference. So what's 1 minus -4? Okay, so the distance here, I don't have any point names, is 1 minus -4. So there are 5 units between my x's. Okay, and I'm going to square them all. There are 8 units between my y's, and there are 10 units between my z's, from 3 to -7. You could again do 3 minus -7, 2 minus 10, it won't matter if I get negative, and 1 minus -4. And when you square all of those, you get 189. And we can, even if we want an exact value, we can reduce the root. So 189 is 9 times 21. And then you can take the square root of 9, take that out. And if you wanted an approximation, you could then put it into a calculator, for example, and write the approximate value there. Again, if you have kind of algebra that you have to solve, it may be useful to write out an equation to solve these, but otherwise it's very straightforward. Something else you may need to do in this particular unit, in the higher level, they jump right into right triangle trigonometry, which I know you've all done. So this might come very quickly, and I'm going to go through it equally quickly, but we can also find angles and sides in relation to each other. In the last couple of things, we were just looking at given distances or points, but perhaps you are given, it's upside down, given a triangle with an angle and you want to know in relation to what's given, lengths or angles, and you're going to need to know these, which we often call SOHCAHTOA, jog your memory, as a mnemonic to remember which trigonometric functions go with which sides to use. So this would mean sine is equal to opposite over hypotenuse, cosine of an angle is adjacent over hypotenuse, and tangent is opposite over adjacent. And remembering the relationship to the angle and the adjacent or opposite can switch, so keep that in mind. I have just a couple quick examples for you on here. In this one, for example, I am given this angle and I want the hypotenuse, and I know the side that's adjacent to the angle. The adjacent one touches the angle but isn't the hypotenuse. So because I know adjacent and I want hypotenuse, I'm going to use cosine because cosine relates those two. Cosine of the angle is equal to adjacent over the hypotenuse. And when I solve this, I would multiply by x and get x cosine of 55 degrees is 23, and then divide by cosine of 55. So one of the tricks is you can swap those out. And for these, for now, you will need to put them into a calculator. So x is approximately equal to 40.1. In this case, we have centimeters. We could also have something like this. I'm going to use this angle. I have the opposite and the adjacent that I want to know or know in relation to it, nothing with the hypotenuse. So I'm going to use tangent. 62 degrees is equal to opposite over adjacent. Here I only need to multiply by 42 to get x by itself. So 42 times tangent of 62 degrees. And then when I put that into the calculator, we get that this side is equal to 79.0 centimeters, approximately. Okay. And in the last one, they want to find an angle, so I can still look at the relationships of sides to that angle, and I have opposite and adjacent, again, nothing with hypotenuse. So I'm going to, again, use tangent. The angle always goes with it here, is equal to opposite over adjacent. And in order to undo trigonometric functions, there is the inverse trigonometric function, which we write here with the -1, and we can just put that again straight into the calculator. Okay, and when you put tangent to the -1 or inverse tangent into the calculator, you get x is approximately 16.9 degrees. Make sure you write that unit there, because when you don't have it, it means something else, and we'll look at that too in a minute.